Welcome to this explainer. Look, if you're a focused learner gearing up for your intensive 45-day generative AI curriculum, you are exactly where you need to be. Before you even think about writing code or, comparing models and building multi-agent systems, you've got to have a rock-solid conceptual foundation. So today we're cutting through all the hype. We're popping the hood to look at the actual architectural engine that's going to transform you into an LLM application developer or an AI solutions consultant by day 45.
Okay, let's dive into this roadmap. First up, the transformer architecture. Then we'll get into mastering the attention mechanism. After that, pre-training and fine-tuning. Fourth, steering with human feedback. And finally, wrapping up with multimodal AI and vision.
Section 1, the transformer architecture, literally the engine of generative AI.
To really appreciate where we're at right now, we have to look at how incredibly fast this industry has evolved. It all traces back to just one single paper from 2017 called Attention is All You Need. That paper, it's been cited over 173,000 times now, which is, frankly, just unheard of in academic publishing. And the reason why is that it completely replaced the slow, step-by-step sequential processing of older architectures with this incredibly elegant mathematical operation. That breakthrough paved the way for the OpenAI GPT series and led to some insane hardware leaps, like Flash Attention 4 hitting over 1,600 teraflops per second.
So the massive fundamental shift here is this. Transformers give neural networks a working memory. See, back in the old days, models like RNNs would process a sequence token by token, reading left to right? But the glaring problem was that by the time the model got to the, say, 512th word, it had pretty much forgotten the first word. Transformers completely solved this by allowing the model to look at every single token simultaneously. It's a real game changer.
Section 2, mastering the attention mechanism, where we really look under the hood.
Now, what's really interesting here is the heart of the transformer, which is self-attention. The absolute crucial takeaway is this concept of learning relevance. The neural network isn't just being told by some programmer exactly how grammar works. Instead, it dynamically figures out which relationships matter. It selectively focuses on the most relevant parts of a sequence when producing an output. Let's break down the exact math happening inside the model. First, every token is multiplied by weight matrices to create three vectors: a query, a key, and a value. You can think of a query as what the token is looking for, a key as what the token offers, and a value as the actual underlying content. Next, we compute attention scores. Then we scale them down so they all sum up to 1, and finally we compute a weighted sum. To put that into perspective, imagine the sentence: the animal didn't cross the street because it was too tired. How on earth does the model know that it refers to the animal? Well, the query vector for the word it scores super highly against the key vector for animal, effortlessly resolving those really tricky semantic dependencies.
But as you might guess, this brilliance comes at a really steep price. 16 billion. Yeah, 16 billion. That's the number of matrix entries generated for a single 128,000 token context window. Because every single token has to look at every other token, standard attention scales quadratically. This means if you double your context window, you don't just double your costs, you quadruple your compute and memory costs. It's a massive, massive hardware bottleneck.
Let's move to how engineers are actually fixing that 16 billion entry memory bottleneck by tweaking the attention architecture. Multi-head attention, or MHA, is the high-quality original standard, but man, it just eats memory. Then you have grouped query attention, which has really become the balanced standard for a lot of those open-source models like Llama and Mistral that you'll use in week 2. But the absolute bleeding edge right now, that's multi-head latent attention. DeepSeek uses this to compress vectors, achieving an astonishing 93.3% reduction in memory cache, and get this, without actually losing any quality. Absolutely wild.
Section 3, pre-training and fine-tuning, the fuel and the steering wheel.
So, the crucial point we need to draw here is the stark dichotomy between building a massive generalist and building a specialized expert. Pre-training is this huge industrial-scale process. We're talking petabytes of raw internet text and thousands of GPUs running next token prediction. Fine-tuning, on the other hand, is surprisingly accessible. You take that massive foundation model and use maybe just a few gigabytes of curated data to adapt it for a highly specific task. This is exactly how you'll build things like the HR assistant or the cybersecurity copilot in your capstone projects.
As machine learning expert Sebastian Raschke points out, the model isn't just memorizing some fixed set of rules. During pre-training, processes called cross-entropy loss and backpropagation actively penalize the model whenever it makes a bad prediction. So, by constantly updating its internal weights to make real continuations from the training data more probable, it slowly but surely internalizes the unbelievably complex statistical patterns of human knowledge, syntax, and style.
Section 4. Steering with human feedback. This is all about aligning the AI.
By day 43 of your curriculum, you're going to dive into responsible AI. And the big question is, how do we take a raw text predictor, which, let's be honest, might generate unhelpful or totally misaligned text, and successfully align it to safely follow human instructions? Well, the industry standard for this is RLHF, or Reinforcement Learning from Human Feedback. It's a continuous loop. First, you collect data of humans perfectly demonstrating the desired behavior, which trains a supervised policy. Next, you have humans actually rank the model's outputs from best to worst to train a separate reward model. Finally, using an algorithm called PPO, or Proximal Policy Optimization, the main model practices generating responses and gets mathematically rewarded by that reward model for being helpful and safe.
And this rigorous training pipeline, it unlocks some serious emergent abilities. These models stop being just simple text predictors and become capable of zero-shot task planning and incredibly dynamic reasoning. They master few-shot prompting and turn into highly interactive conversational agents. This is exactly what's going to let you leverage frameworks like LangChain to build your own autonomous AI agents in Week 6.
Section 5. Multimodal AI and Vision, taking us way beyond just text.
In Week 6, things get incredibly visual. There was this fascinating realization in the AI community that the exact same transformer architecture we use for text can actually process the physical world. Just imagine taking distinct, trimmed support videos, like different little clips of ice skaters, and using them to process and map an entirely untrimmed query video sequence. The attention mechanism here isn't looking at text tokens anymore. It's looking at image patches and video frames, literally mapping relationships across spatial dimensions and time.
By treating these image patches as a sequence and utilizing positional encoding, vision transformers are totally revolutionizing computer vision. They are now capable of deep scene and situation understanding. They can analyze spatially distant relations, which is just incredible for things like complex sports analysis, and they understand long-range temporal interactions in video. It just proves that the underlying math of self-attention is entirely adaptable.
So, you might be wondering, why does all this underlying theory matter for your 45-day curriculum? Because understanding this architecture is the absolute foundation of everything else you're going to do. Whether you're chaining together multi-agent workflows, designing RAG pipelines with Pinecone and Llama Index, or building full-scale enterprise apps, knowing exactly how the engine works under the hood makes you a vastly superior developer. You now understand the engine, the transformer. You understand the fuel, the petabytes of pre-training data. And you understand the steering wheel, RLHF. As you approach the end of your intensive curriculum, the only real question left is this. Which capstone project are you going to build first? Are you going to tackle an AI interview coach? Or maybe build a fully autonomous cybersecurity co-pilot? The tools are all right there in your hands. Get out there and build something amazing.